frequency will oscillate at, I mean, it's plus or minus, so it doesn't matter. So omega I plus omega j plus omega k. So please make a DC shift here. So make this addition 0, okay? But while doing that, you don't have too much freedom. Why? Because we already steered the QIJs, we don't want to disturb. Look here, when we were steering QIJs, we didn't want to disturb QIs. By the fact that these are sinusoidal, there will gonna be no net shift in QIs, right? Because the average of sine and cosine is 0. When we come here, we will create a QIJ shift in QIJK, but we don't want to disturb the QIJs, which means we don't want this to be 0 for any combination. So we want this to be 0, but we don't want omega I plus omega j to be 0, or omega I plus omega k to be 0, because this will create motion along the corresponding Lie bracket, and q omega j plus omega k to be 0. Okay, we don't want that, right? So this is the main point, the main strategy laid out by Mori and Sastry, as you can see. It's very natural, it's a very highly cited paper actually. Any question about that? We'll have an example later. Any question so far? So let's see, here's an example from their paper.
So, Professor,
yeah.
Can you go up a little bit?
Sure.
So for steering the QIJs, we just excluded the case where omega I plus omega j equal to 0, right? So we're left with omega I minus omega j.
You can have either, it doesn't matter. It will change the sign of the sign waveform, right?
But we just excluded that for steering. That if I want to steer both simultaneously, I have to.
They don't do it simultaneously. This is their strategy. Finish this first, then finish this guy, and while doing this guy, your planning should not affect what you achieve there, and so and so. Yes, they don't do it simultaneously. Okay, so here is an example. Q1 dot is U1, Q2 dot is U2, Q3 dot is Q2 U1, I just labeled them Q1, 2, 3, 4, 5, not in their way, and we need to figure out their labeling on our own. So this is Q3 U1, and this guy is Q3 U2. So in our language, this is something times U1, something times U2. Here is 1, 0, Q2, Q3, and 0, 0, 1, 0, 0, Q3, right? So this is G1, G2, and the Lie bracket between G1 and G2 is, I guess it's 0, 0, 1, and negative Q1 and 0. So you can see here I can achieve motion directly along Q1 and Q2. Along Q3, it needs a Lie bracket, first order Lie bracket between G1 and G2. And if you take a Lie bracket, say this is V, if you do Lie bracket of G1 and V, for example, you get actually 0, 0, 0, it's the fourth coordinate, I guess it's 2. And if you do it with G2, these are all arrays, you get the fifth direction. So we have here the fourth, the fifth. Okay. So let's do the planning. Let's do the steering here. They said first steer Q1 and Q2, and you don't need any advice to do it, right? Steer Q1 and the Q2 directly, that's okay. Second, let's steer Q3, which needs motion along the Lie bracket G1 and G2, right? Any suggestion here, what is U1 and what is U2? Any suggestion? Any suggestion?
One is cosine, the other is sine.
Yeah, so this guy is, say, sine omega. So this is B cosine what? The point is, this guy, so let's see, this guy will oscillate, and this is omega 1 and omega 2, so here is omega 1 and omega 2t. This guy will oscillate at what frequencies? This guy oscillate at what frequencies?
omega 1 plus omega 2.
Yeah, omega 1 plus or minus omega 2. So the obvious choice is to take them equal. So this is omega and omega, right? Okay? So always the Lie bracket, first order Lie bracket is easy. It's A sine omega, B cosine, the same omega. And it doesn't matter who is which, who is cosine, who is sine, doesn't matter. Why? I mean, if it's not obvious, let's check it here. It's super easy. Well, here is Q3, right? This is your Q3. It comes from Q2 and U1. Okay, so here is my U1. Let's get Q2. Q2 is the integral of U2. So here is the integral of U2. Let's integrate this, please. If this is cosine, the integral of cosine is B over omega sine, right? And now Q3 is the integral of Q2, which is B over omega sine, times U1, which is A times another sine, right? So you see here how it's the matching sine and sine of the same frequency gets you sine squared. When you integrate over the period, you get something. You get here actually AB over omega. You get half of the average, and you get the period, which is 2 pi over omega. So you get AB over omega squared. We always get this from averaging. We will come to it later on averaging amplitude squared over omega squared. So, any question about that? About this tuning? Because you're going to do it in homework. This is not hard. Let's do the third, which is, it's also not hard, but let's do it. Steer Q4, for example. Let's give it a name in order to, because this is actually motion along this Lie bracket. It was G1, G1 with G2. So, naming wise, it's actually 112 or 121 because you can play around, right? So, let's give it a name. So Q4 coming from Q3, so let's give actually a name for Q3. Q3 was Q2U1. According to their naming, this is our 3, it's Q2U1, so this guy is actually 2-1, right? So Q3 is actually 2-1, Q21. And in this naming, this Q4 is 2-1-1, okay? So this guy is Q211. Any question about the naming? I mean, it's super easy. Okay. So if U1, I have just two inputs, U1 and U2. So actually U1 is A sine omega 1t, U2 is B cosine omega 2t. Can you tell me please Q4 or this guy will oscillate at one frequency? At what frequency? What frequency? Forget about the subtraction, let's add them. What frequency?
2 omega 1 plus omega 2.
Omega, you said what?
2 omega
2 omega
1.
1, very good, yes. 2 omega 1 plus omega 2, exactly. And we need to make a DC shift, so this needs to be 0, that's it. Okay? It's as easy as this. So this means that U1 is A sine some omega, and from this equation, this guy is actually twice the omega. It doesn't matter the sign. It will just make you move along forward or backward along the Lie bracket. You will need to reverse it anyway when you do sideways. Okay? Any question, guys? So in similar way, you can oscillate Q5, which is actually 2 Q2 1 2. Okay? Do it the same way. It's the other way around here. Any question? Any question? Is it clear enough for what? I mean, next time we'll have a much harder steering algorithm. This is obvious actually. But I mean, feel free, because sometimes, well, it took me a while to understand it, so maybe I'm not conveying it in the right way, but feel free to ask questions, please. Have a question, feel free to ask. Need to have an adult conversation. It's an advanced credit course, so we need to raise questions for research points or so. If you have a question, come up with it, please. In the same paper, they generalized it to what they called chain systems, and when you look at it the first time, you realize, wow, it's so constrained, but actually it's not. It covers a wide range of nonholonomic systems. We're going to see here in a minute. So this is the form of their systems. Qi dot is Ui, as we know. No, sorry, it's Q1 dot is U1. It's very specific. Q2 dot is U2. And then anything else is governed by U1 times the previous state. So Qn dot is Qn minus 1 times U1. So in our language, this is 1, 0, but then all the states ordered. So this is Qn minus 1. And the other one is just 0, 1, and all zeros. So you can see right away that the Lie bracket between G1 and G2, the kth order Lie bracket, is actually at the origin, is actually 0, 0, all the way here, negative 1 to the k, and zeros. And this is the k plus 2 entry affecting the q k plus 2. So if we have, their proposed solution is a sine omega t, and to have this synchronization, it is b cosine k omega t. So the Q3, which comes from a first order Lie bracket, you're gonna have addition and subtraction. Addition is always, it's higher, so let's focus on subtraction here, and it doesn't matter, addition and subtraction. K minus 1 omega, right? Q3 will oscillate at k minus 1 omega, because it's the first order Lie bracket. So it's just multiplication one time, so you get the addition frequencies and subtraction. Q4 will oscillate at k minus 2 omega,